Okay, the previous one was only one step. This one is a lot more steps here. This one is, the pressure in an automobile tire is 29 psi on a day. The weather report states that the barometric pressure is 30.09 inches of mercury. How would you report the absolute pressure in the tire to a colleague in kilopascals? And so this one is a lot more, orders of magnitude more involved in the previous problem. So this is quite a big step up. And so to answer this problem, we need to go back here and talk about this. This is something I skipped earlier. There's something called gauge pressure. It's the pressure on pressure gauges typically. But we have two types of gauges. We have gauges that measure gauge pressure, and we have gauges that measure absolute pressure. The difference is like this. Let's say we have a helium tank. So it's just filled with gaseous helium. What should I say, gaseous helium atoms or gaseous helium molecules? Let's say atoms. A bunch of helium atoms in here. Let's put a pressure gauge on here. Two types of pressure gauge. So I'm going to have is one pressure gauge is going to be labeled PSI-G. Or I can buy a pressure gauge that's labeled PSI-A. We'll measure the same helium tank using these two different gauges. All right, the first one, what do you think G and A stand for? Gauge and absolute. And so the first one here is PSI-G. And the difference is most people are used to PSI-G because of this. When the helium tank goes empty, right, what's the gauge pressure on it? The helium tank goes empty, the gauge pressure should be, what do you think? Helium tank goes empty, the gauge should read 0 psi. There's no more helium left, right? And so what we should see is 0 psi. PSI-G we'll call it. But is that tank really empty? I mean, in order to be really empty, we would have to make sure that all of the helium is sucked out of there, because to be really empty, it has to be empty space. And so hopefully the helium tank is built like this. This is we call a vacuum chamber. It's built of heavy stainless or heavy duty Monel, very thick wall. Very thick wall because you don't want it to implode. Wow. And then you can suck the gas out of here. But even with this ultra high vacuum, can you suck all the gas out of here? Has anyone made a perfect vacuum on Earth? No. And so if this is reading 0 psi, you know what it means? It means that there's 0 pressure difference inside the tank and outside the tank. What we need for the helium to leak out is we need more pressure inside, less pressure outside. If there's more pressure inside, then the gas will be forced out of the tank into the lower pressure air out here. However, if the pressure of the helium inside here is the same as the pressure of the air outside here, then there's going to be 0 pressure difference. And so this is measuring the pressure differential. In other words, there's still helium in here, but there's going to be how many psi of helium? there's still helium in the air, but it's going to be at 15 psi. Because if there's 15 psi of helium inside the tank and 15 psi of air outside, then no gas should escape. And so we call the tank empty. But it's not really empty. In order to make it really empty, what do we have to do? We have to hook this up to a vacuum apparatus and then suck the remaining helium out of there using a vacuum pump. And so in order to suck if we could suck all the helium out of there, let's say the barometric pressure of the day, in other words, the atmospheric pressure of the day is 760 millimeters of mercury, which is 14.70 psi. Let's say that's the barometric pressure. What we'd have to do is we'd have to suck all the remaining helium out there. If we do that, the gauge goes negative, and we end up at minus 14.7 psi G. If we end up at minus 14.7 psi G, we've sucked all the helium out, and now we have a perfect vacuum inside here. When you buy helium and you buy it in these tanks, what we do is when we run out of helium, we ask them to refill the tank. We don't throw away the tank. You know, the home tanks you throw away, but the tanks we use, we keep because they're very expensive tanks. But the situation is this. If you refill and you return the tank really empty like this, that is, the gauge reads 0, they're going to charge you an extra fee. They're going to charge you an extra fee because of this. They always want the tank returned with a little bit of pressure in there. They always want the tank returned with a little bit of pressure because that way they know nothing leaked in. The only thing that's going to happen is gas is going to leak out of the tank because there's more pressure inside than outside. If the tank reads 0, then they don't know, because if it reads 0, that means the valve was open. And how long it was open? Because if it was open for a long period of time, air will leak in and helium will leak out, even though the pressure is the same. We have a process called diffusion. And so what it's going to do is it's going to contaminate the helium. And so if you really return the tank at 0 psi G, you get charged an extra fee, because what they have to do is they hook it up to a vacuum to suck out any contaminated helium out of there. They don't want any contaminated helium in there. So they hook it up to a vacuum, but do they have a perfect vacuum? They don't have a perfect vacuum, so what they got to do is they got to do this. They use a high vacuum. They suck out most of the helium, and then they backfill it with pure helium. But it's still not clean, so they suck it out again, and then repeat. And so they're doing multiple rinses of the tank using pure helium or clean helium. And so this is why the extra charge, because they have to get rid of any air that might have contaminated the tank. And so we don't let it go. But anyway, when you buy a tank of helium, it usually comes out to like 2,000 psi G. Well, we want a lot of helium in there, so 2,000 psi G. What would this look like on the psi A? So if we're at minus 14.7, what is the absolute pressure of that? Minus 14.7 psi G would be equivalent to what psi A? Minus 14.7 psi G means this. This is called vacuum here. And so we're at minus 14.7 psi vacuum. It would correspond to 0 psi A. That is, there's no gas in there. And so 0 psi A, and if we're at 0 psi G, that means we're at 14.7 psi A. And if we're at 2,000 psi G, then what are we at in terms of psi A? What is the psi A? Here. What is it? 1985.3. Go the other way. Go the other way. $24.7 PSIA. Do you see the relationship between PSIA and PSIG? The only difference is the zero. This is what we call an arbitrary zero. This zero just means it's the same as barometric pressure, the same as atmospheric pressure. The zero, the gas in here. There's still gas in here. This is what we call absolute zero. This absolute zero means there's nothing in there. And so absolute versus relative. The relative, it's based on the gauge. Absolute is based on having no gas. We've seen this before because we solve equations, like this. And the relationship between this is this, that the PSIA is equal to the PSIG plus the atmospheric pressure. Because it's the way the gauges work. If the atmospheric pressure and the gas pressure are equal, then it's going to be zero. And so as the atmospheric pressure changes, so does the gas pressure to make it equal to zero. Here. And so in other words, it's offset. We've seen the same thing happen, with the Celsius and the Fahrenheit. Do the Celsius and Fahrenheit have the same zero? No. In fact, we know that for Fahrenheit, we have to add what to it? We have to add 32. Are the Kelvin and Celsius temperatures the same? Zero? No, the zeros are offset by 273.15. So therefore, in order to get the Kelvin temperature, we have to add 273.15. Well, the same thing here. The zeros are offset by, in this case, 14.7. Therefore, to get the PSIA, we need to add 14.7. But based on the design of this gauge, the way the gauge works, the atmospheric pressure can change day to day. If atmospheric pressure changes day to day, the zero is referenced just to the atmospheric pressure because there's just some diagram in there that pushes one way or the other. And so whatever the atmospheric pressure of the day is, that's what zero is on the gauge. So, it varies. So you want it filled on the day when the atmospheric pressure is. So let's go back to this problem. There. Okay, this problem is complicated in a number of ways. So one, these are gauge pressures. This is gauge pressure. Automobile tire. When an automobile tire goes to 0 psi, did they suck all the gas out of there with the ultra high vacuum? No. If it goes to 0 psi, that means that there's 14.7 psi left of the tire. And so this is gauge pressure. And so this has got to be 29 above whatever the pressure is of the day. Now the pressure of the day, they can write in any units. In this case, typical weather report will be in inches of mercury. And so, and then they want the absolute pressure in kilopascals. Now some tires, especially the European tires, bike tires, will have kilopascals rather than PSI, or both PSI and kilopascals for pressure. And so what we're going to do is first we have to figure out what we do with this. And so the absolute pressure is going to be the gauge pressure plus the barometric. But the units are different, so we've got to make sure the units are the same. So we can convert PSI into inches, or inches into PSI, or PSI into kilopascals, and then inches into kilopascals, and then add them, or subtract them, or whatever. So why don't you give this problem a go, and then see what you get for the answer. And so I'll just write some of the conversion factors. 1 atmosphere is 29.92 inches of mercury, and it's equal to 14.70 psi, which is equal to 101,325 pascals exactly. So give this a go and see. So in other words, let's go ahead and overlay this. If it's minus 14.7 psig, it's going to be 0 psia. If it's 0 psig, it's going to be 14.7 psia. And if it's 2000 psig, it's actually 2014.7 psia. But you're never going to get this last 14.7 out of there. You're not going to get this out of the tank unless you suck it out of the tank. And so that's why the tank only reads 2000, because this remaining 14.7 is never going to be recovered. Does that make sense? Yeah. So give this a try. Let me know if you suck. But do you know what type of problem this is? This is a combination of dimensional analysis and algebra. I'm going to use both to solve this. So first start off with a dimensional analysis. 301.7. You got the same thing. Kilopascal. Actually, let me. So let me just say, this is a combination of dimensional analysis and algebra. So the first part is the dimensional analysis, converting PSI into kilopascals. Have you seen this conversion factor? Have you seen that before in the book? No. And your book likes to do this. Your book likes to combine conversion factors to get new conversion factors. But I don't recommend that. I don't recommend that because it's an unfamiliar. That looks unfamiliar. I mean, maybe you can see it right off, but if you're used to seeing certain conversion factors over and over, then it's a lot more familiar. So dimensional analysis, we need to get rid of PSI. Sometimes we would label this, this is actually PSI what? A or PSI G? This is PSI G, so sometimes we'll just label it so we don't get it mixed up with PSI A. That way we won't get this thing screwed up. And so, let's call it G. And so if we want to get rid of PSI, how can we get rid of PSI? Put the G in parentheses. Well, I know that for PSI, I just know 14.70 PSI per atmosphere. And so the PSI cancels, and that leaves me with the atmospheres gauge. And so if I had a gauge that read atmospheres, gauge pressure, then that would be it. And now I need to get rid of atmospheres. But I can get rid of atmospheres and go to a lot of different things. I could go to millimeters of mercury, I can go to inches of mercury, etc. Where should I go here? Should I go to inches of mercury, 29.92? No, I should go to pascals. So I'm going to write 101,325 pascals here for 1 atmosphere. And then I need to get rid of pascals. Where should I take it? To kilopascals. And so as far as that goes, there are 1,000 pascals in every kilopascal. And so the pascals cancel. Atmospheres cancel, and this gives us the kilopascals of gauge pressure. So, doing that, what did you end up with here? Well, actually, it's 2.0, but I don't like it written like that because I want to see how it was rounded. So 29 divided by 14.7 times 101,325 divided by 1,000. I get 199.8. Now, how many sig figs am I allowed? This is kilopascals gauge. I'm only allowed 2 sig figs, so this is really 1979.8 kilopascals. I'll carry 2 extra digits. Avoid round off here or there. And then the barometric pressure was 30.09 inches. And so this is the first dimensional analysis. The second dimensional analysis is the 30.09 inches of mercury here. And the same thing here. You probably can see that this is a composite of conversion factors here. I mean, composite of conversion factors, I don't recommend that. I recommend just using familiar ones. These are the ones we want to kind of drill in and remember. Although you don't have to memorize these. It's just for familiarity. And so we're going to go from inches of mercury to what? Yeah. So 29.92 inches of mercury is 1 atmosphere, so inches of mercury cancel. Now, is this gauge? No, this is barometric pressure, the atmospheric pressure. And now we need to get rid of atmospheres. How do we get rid of atmospheres? I'll just go to pascals, 101,325 pascals per atmosphere. Atmospheres cancel. And then we'll go to kilopascals. So 1,000 pascals per kilopascal. Let's get this. This is going to be 30.09 divided by 29.92 times 101,325 divided by 1,000. This gives us 100. And how many sig figs are we allowed here? 4. So 101.9 kilopascals. Okay, now what do we do here? If we want to figure out the absolute pressure, we have to do what? We have to add them together. The absolute. See, the gauge is not going to show this. The gauge is not going to show this 100 kilopascals because in order to use that air, you would have to suck it out with a vacuum. And so, well, we want the total, so it's going to be 199.8 kilopascals of the gauge plus the barometric pressure, which is 101.79. If I look at kilopascals, barometric or atmospheric pressure. And so the total pressure here is going to be 301.7, was it? Yeah, 301.7. But if I look at the uncertain digit, the uncertain digits is going to be here. So we're really only allowed 2 sig figs. So we'll round it to 3.0 times 10 squared for 300 kilopascals. So the absolute pressure is the gauge pressure plus that little bit left over in the tank. That little bit left over in the tank is the atmospheric pressure. In this case, it's not such a little bit left over. It's quite a lot left over in the tank. And so we add the two together, make sure we get the sig figs right. And we're okay. All right, any questions on this problem? I didn't give you enough time, but I need to finish up this chapter today, so I just want to keep moving here. All right, the next section, I skipped a slide here. I didn't skip a slide. It's the next section is what do we do in science? We take observations. So these are observations of volume and temperature. But the volume is really weird because they're measuring the volume by the height. And so I guess the higher this is, the bigger the volume, the lower it is, the smaller the volume. This is a mercury plug. So there's some gas trapped in here. So they can just measure the height. And so what they're going to do is they're going to relate, the higher it is, the bigger the volume because the area stays the same. And so the volume is the area times the height. Since the area is not changing, just the height is changing, it's going to be directly proportional to the volume. And so rather than plotting the volume here, they're just plotting the height. And so how many data points did they take? Well, probably one here, 22. The lab was probably 22 degrees. And so they measure the height, 75 millimeters. And then warm it up to 50 degrees C. If they warm it up to 50 degrees C, then they see the gas expanded. The height is now 82 millimeters. And then they cool it down to 0, probably in an ice bath. An ice bath is a good way to get 0. And it shrinks. And then they cool it down to minus 15, which is a bit more challenging. Cooling it down to minus 15 shrinks more. And so we have 1, 2, 3, 4 data points. And so it's hard. Do you see the pattern in the data points there? It's hard to see it in the table like this. Is it linear or non-linear relationship here? And so what's done is you take the data, do the observations, and then you might try graphing it. If you graph it like this, and here are 4 data points, and you see they're all on a straight line. And so we call this a linear relationship. we take probably more data here because sometimes it can start off linear and then go non-linear. But in this case, if we take more data down here, we see it just lines up with the rest of the data, so this is linear. And so this is a linear relationship between volume and temperature. And so what we can do with something like this is a different thing. One, we can see, what the range is. As far as the height goes, what's the smallest height we can have? It goes down to 0. So if the height goes down to 0, the volume goes down to 0. And it looks like the temperature, which the volume goes down to 0, is minus 273.15 degrees C. Can we go to negative volume? Is that possible? Is there such thing as negative volume? Let's say you're on a low sodium diet. If you're on a low sodium diet, can you have like negative 2 grams of salt? I want negative 2 grams of salt for lunch, and then I can have 4 grams of salt for dinner. Does that work? There's no such thing, right? It's like a milkshake. I want a negative large milkshake, and then I'll just have a small milkshake. No, so there's no such thing. So, the smallest volume that's possible is here. That means the lowest temperature possible is minus 273.15 Celsius. There's no such thing as minus 300 Celsius, is there? Could you have minus 300 Celsius? Could anything be at minus 300 Celsius? What would that mean? What would that mean is this. At 0 Kelvin, or minus 273 Celsius, what happens to motion, kinetic energy? It stops. And so motion stops here. Now, can we have reverse motion? Reverse motion means that this. If we were to go negative 300, then something has to happen because all of a sudden we go from motion to no motion. Now, if we go negative, what does that mean? Does that mean that, in the positive, it was moving forward, in the negative, it moves backwards, everything moves reverse? Is that the case? No. And so we define a new temperature scale. The new temperature scale is going to define this as 0. If we define this as 0, there's no such thing as negative temperature, only positive temperatures. And we call this scale the red scale, not degrees C, but Kelvin. So this is the Kelvin scale. The other thing is we look at the relationship. So for example, if we double the temperature from 100 to 200 Kelvin, going from 100 to 200 Kelvin, what happens to the volume? The volume doubles. So if you double the temperature, the volume doubles. So we see that kind of relationship, mathematical relationship, which is a linear relationship. And so from this plot, we get something called absolute zero. Absolute zero is the lowest possible temperature of 0 Kelvin, which is equivalent to minus 273.15 degrees C. This is where molecular motion stops. This is the particulate view, theoretical view. And it also corresponds to 0 gas volume. You can't have negative volume. And so according to kinetic molecular theory, the average kinetic energy of the substance is 0 at absolute zero. There's no motion. I shouldn't say there's no motion. There's no atomic motion. There are electrons inside atoms. So electrons never stop, and that's called the 0 point energy. We'll talk about that later. At the particulate level, we can see it here. The higher temperature means more forceful collisions inside here. If this is hot and outside is cool, then it's going to generate greater pressure inside and force the volume up. But we don't have to really worry about that. So volume is only proportional to the absolute temperature. It's not proportional to the Celsius temperature because the scale. It has that arbitrary 0. We could make it, proportional to the Celsius temperature. We could say this is volume is proportional to the Kelvin temperature. Because at the Kelvin temperature, what is the y-intercept? If we use the red scale, what is the y-intercept? 0. And so at 0 Kelvin, we have 0 volume. However, if we use the black then y, if we use the red, y is equal to mx plus b, b is equal to 0. And so mathematically, this is it. B is equal to mx plus, or y is equal to mx plus b, but b is 0. And so we have to use the Kelvin temperature if we want to get rid of the b. If we use the Celsius temperature, then y is equal to mx in Celsius plus, plus a negative 273.15 degrees. And so we have to tack on the b term here if we use the other scale. So we could do this either using Celsius or Kelvin, but it's a heck of a lot easier using Kelvin because we don't have an equation like we had for the Fahrenheit. Degrees Fahrenheit is equal to 9/5 degrees C plus 32. So if we can drop the intercept, then it looks like this. Well, if it looks like this, then what we can do is we can rearrange it. And so V over T is equal to constant. And so the volume and temperature ratios, if the volume to temperature ratio is a constant, then we could do this. If we end up changing something, the ratio must stay the same. And so we end up with something like this here. So what happens is this ratio must stay the same. So if we double the temperature, what must we do to the volume to keep the ratio the same? And so if we 2 times the temperature, we better 2 times the volume, otherwise the ratio is going to change. So if we double the temperature, the volume doubles. If we triple the temperature, the volume should triple to keep the ratio the same. That's what we call directly proportional. And so double the temperature, the volume doubles. It's directly proportional. That's what this will be. But anyway, I don't really worry about all these equations. I just worry about the last one. And so this is the mathematical relationship that's quite useful that we derive from that plot. And this mathematical relationship is called Charles' law. Charles' law is just an empirical equation that comes from that data. And Charles' law, he developed this in 1787, so like a number of years ago. So Charles' law here, this is the form you want to remember for Charles' law. V1 over T1 is equal to V2 over T2. And so we look at the use of Charles' law. Let me just blast through these slides here. A container with flexible walls holds a gas that is cooled from 65 degrees C to 22 degrees C with no change in pressure. If the container volume was 4.5 liters initially, what is its volume after being cooled? And so what we can do is we can say this. We see T1, we're going to say is 65 degrees C. And then T2 is 22 degrees C. And then V1 is 4.5 liters. And then V2 is what we're trying to solve for. And so what we're going to do is we're going to rearrange Charles' law to this. V2 is equal to this. I'm going to put T2 over T1 times V1. All right, I can leave it at Celsius, but I need to add that term, plus a negative 273.15, but that's too much hassle. What's much easier is just to convert from Celsius into Kelvin. That's much easier than using a more complicated algebraic expression. So I'm going to go ahead and convert this by adding 273. So 273 plus this is going to be 338 Kelvin. And 273 plus this is going to be 295 Kelvin. And so T2 is 295 Kelvin. T1 is 338 Kelvin times V1 at 4.5 liters. And so here, what's happening is the temperature is decreasing. If the temperature is decreasing, this is what we call the temperature fraction. The temperature fraction is going to be less than 1, which means the volume should shrink. And so what's the volume going to come out to? And we'll do a 295 divided by 338 times 4.5. And I get 3.92. 3.92 liters, which just goes around to 3.9 liters. Okay, here they rearranged the equation. They didn't get the temperature fraction. I'd like to get the temperature, so I'd like to put the T2 over the T1. Here. I don't necessarily like the way they set it up. Here they did the conversions to Kelvin inside the equation itself. It is separate. They get 3.9 liters as the final answer. So yeah, the volume decreases because the temperature went down. So that's Charles' law. Two more laws here. This one is Boyle's law. Boyle's law, he did the pressure volume. When you look at the pressure volume, you look at what is the pattern here. Well, when we look at the pattern, is that linear or non-linear? This is non-linear, so the equation is a little different. We don't have y equals mx plus b here, but it turns out the math is not that hard for this one. And so what happens is, as the pressure increases, the volume decreases. And so what that means mathematically is this. The volume is inversely proportional to pressure. As the pressure gets bigger, the volume gets smaller. And so we end up with an equation that looks like this. And then we can rearrange it to an equation that looks like that. And since that's equal to a constant, the product is going to be the same. So we end up with Boyle's law. This is Boyle's law. Boyle's law is that P1 V1 is equal to P2 V2. This is Charles' law. So let's look at the sample problem here. A gas sample occupies 5.18 liters. So V1 is equal to 5.18 liters. At 776 torr. So P1 is equal to 776 torr. Find the volume of the gas if the pressure is changed to 827 torr. So P2 is 827 torr. So what we want to do is we want to find V2. So we're going to solve this equation for V2. V2 is equal to P1 over P2 times V1. And so this is called the pressure fraction here. So if we take a look at the pressure increased. And so if the pressure increased, so P1 is 776 torr. P2 is 827 torr. Then the pressure fraction is less than 1. So the pressure increases, we expect a decrease in the volume. And that makes sense. The greater the pressure, the smaller the volume. Volume is 5.18 liters. So this is going to be 776 divided by 827 times 5.18. And I get 4.86 sub 0 liters. And we can round that to 4.86 liters. And so pressure goes up, volume goes down, 4.86 liters. Here they did pressure fraction. Do you see that? T1 over T2, pressure fraction. 4.86 liters. That's what they got. I don't remember Charles' law. I don't remember Boyle's law. You know, just for a historical perspective and the scientific method, we talk about it. But what we do is instead we combine it, because Charles' law says volume is proportional to temperature. Boyle's law says volume is inversely proportional to pressure. And so we can combine the two together when we combine the two together, then we end up with something like this. You know, pressure times volume over temperature is equal to constant. So that ratio is always a constant. And so we end up with a combined gas law, which is this. P1V1 over T1 is equal to P2V2 over T2. So you don't have to remember Charles' law, you don't have to remember Boyle's law because it's incorporated in here. For Charles' law, if we go back to the Charles' law problem, let's take a look at the Charles' law problem really quick. Here. Take a look at what they said. They said this. In the Charles' law problem, they said, with no change in pressure, if the pressure doesn't change, that means P1 and P2 are the same. So if P1 and P2 are the same, what does that look like? It looks like Charles' law. So if the pressure cancels, then we have Charles' law if the pressure doesn't change. Let's look at Boyle's law, the problem we looked at. Boyle's law says the temperature remains constant. If the temperature remains constant, then T1 and T2 cancel, because they're the same number, and we have Boyle's law. So I don't have to remember Charles' law, I don't have to remember Boyle's law, I just have to remember the combined gas law. Now, what they're saying is the amount here. The amount remains constant. Why are they saying the amount remains constant? They're saying the amount remains constant because when you get to Chem 1A, you don't even bother with this one. You bother remembering this version of the combined gas law. P1V1 over N1 T1 is equal to P2V2 over N2 T2, where N is the amount. And so not in this class, but in Chem 1A, you'll have problems like this. A little bit of gas leaks out. If a little bit of gas leaks out, then how does that impact the pressure, temperature, volume? And so the amount changes. But in Chem 4, we aren't going to have the amount change. Just in probably just in Chem 1A. And so this wasn't really necessary because in all our problems, the amount remains constant, I think. I don't think there's a problem in the book that has the amount changed. And so that's Boyle's law. There's a problem with Boyle's law. I think we just did it. Did we? Oh, the combined gas law. There's a problem with the combined gas law here. We'll finish off with this problem here. A cylinder in an automobile engine has 350 cubic centimeters. This engine takes air at 21 degrees C and 0.945 atmospheres of pressure. And so we'll just do V1 is 352 cubic centimeters. T1 is 21 degrees C. 21 degrees C is 294 Kelvin. And P1 is 0.945 atmospheres. Okay, then we'll go on here to V2 is unknown. T2 is 95 degrees C. 95 degrees C is plus 273, which would be 268 or 368 Kelvin, sorry. And then the pressure is 4.95 atmospheres. Okay, then we solve the combined gas law for V2. So V2 here, we'll do the pressure fraction first, is P1 over P2. Then we'll do the temperature fraction, which would be T2 over T1 times V1. And so when we look at the pressure did what? The pressure increased. The pressure increases, then the fraction should be less than 1. So we have 0.945 atmospheres over 4.95 atmospheres. And so this is less than 1, decreases. And the temperature increase. If the temperature increased, then the volume should increase. So the temperature fraction is greater. And so that's going to be 368 Kelvin over 294 Kelvin. And times the original volume of 352 cubic centimeters. And so let's just do this one really quick. I'll end with this one. 0.945 divided by 4.95 times 368 divided by 294 times 352. that gives us, if I did everything correctly, 84.11 cubic centimeters. So the volume decreased because the pressure fraction was a lot less than 1, whereas the temperature fraction was a little bit greater than 1. And so let's see if I did that right. Yeah, 84.1 cubic centimeters. Okay, there is one more law. Oh no, I gotta talk about STP next. Oh, I ran out of time. I won't keep going. I'll talk about STP later. All right, that's it then. Went a little over.